Cool. So I'll start from here. What are we gonna solve in this episode is basically KV cache. The point is at every decoding step, we are recomputing the entire input IDs, like the all the input IDs that we had, and we are concatenating it, and then we are recomputing it from start to end. For example, if we had like 50 token generation and there was like a 10 token prompt. So step 50, we'll have to recompute attention for all the 59 previous tokens, even though their keys and values had not really changed. So the idea of KV cache is to store those computed KV tensor and reuse them, right? So what exactly is happening is, consider this part over here. So this is where we are actually computing. So what happens at step 0? Let's say we are at step 0. This is the part when the user has actually given us this initial prompt. So we have not started actually generating anything. So we will start with token 0, token 1, and token 2. And this will be passed to the forward function like we are doing it right now. This is the first decoding step, right? And we'll have to like compute the KV cache KV for each of the tokens right here. Uh, in the step 2, the same, in the step 1, the same will happen. It's just we'll get token 3 as well. And where are we getting this token 3 from? We are getting it from here. We'll get token 4 here. Uh, and the same will go for the next step. Let's say this call this token 4, and then this is token 5 as the output. Notice how this token 1 2 was actually computed in the previous step, and in this step 2 we already had the KV values for token 3. So yeah, that's the entire idea. The idea is that this function will also give us a KV cache, or basically the value of KVs, right? So it will be a tuple of k comma v, and yeah. So instead of just passing token 3, we'll pass token 3 like this, and then we'll also pass KV cache. So we'll get token 4 as the output, and the same goes over here. We'll have token 4, and then we'll pass KV cache, and KV cache is here. So this is how the things are gonna look like. Exactly like this. So let's start from, this is a function that's actually handling the internal. So the forward function is actually implemented in base model. We'll go in the model.py. Where we'll see that we have Llama block and Llama model. So Llama blocks is just repeated in the Llama model over here. Let's start with Llama block. In Llama block, we have GQA, the main part. So we'll go inside GQA, and yeah, let's start implementing. What is the main idea over here? The point is, this forward function should implement, should accept past KV values as the input. But what is this past KV going to look like? This is, as I already told you, it's going to be a tuple of, for not 2k, it's tuple of torch dot tensor comma torch dot tensor, right? I think tuple does not need these brackets. It's not callable really, right? And that is why I don't like using this thing. But we can also have like none, and by default the value will be none. Now, cool. Let's just Oof. Start this up. I don't know why my ref is not working, but okay, that is not an issue here. So after we have this rotary embedding, we need to update our key and uh, like values and the keys. So the we first need to unpack the past k and past v from the past kv, and we need to ensure if past kv is not none, then we'll do this. And then our final k is gonna be concatenation of past k comma k, and the same will go for our values, past values. This. Now, along which dimension this concatenation has to happen? See, the key has dimension of v comma t comma num kv heads comma head dim, right? No, actually it's transpose 1 2, so I'll do this. It's like this. Yeah, this t is actually sequence length over here. uh, Now if our total sequence length that we have already processed is like the past k, like the past kv will look like 1 comma 8 comma let's say it was 12 comma 64. So 12 was the sequence length that we have processed until now, and since we are concatenating it, so our new dimension is going to look like 1 comma 8 comma 13 comma 64. And we are always processing only single step at a time during decoding, so the increment will always be 1. And the point is the concatenation has to happen along the second dimension. So I can write here as dim equals 2. Correct. Similarly over here, dim will be 2. Right. Let's move ahead. Okay, now we have this squeeze, expand, and reshape. The point of this is, say, we have implemented GQA over here. So these keys and values have to be uh, repeated n number of time for each of the query head, so that we have total number of heads. For example, the kv that we have in llama is basically 8. So k comma v in llama uh, k comma v in llama head is 8, and the query head that we have is 4, or the number of groups we call them groups is 4. So effectively total number of head that is required is 32, because 8 times 4 is 32. So yeah, that is what is supposed to happen. That is what is supposed to happen. So we need to change, like the only thing that's gonna change over here is this t value, because the value of t is always going to be 1 here. Why 1? Because of x dot shape. So this is going to, how is it going to look like? It is supposed to be something like full sequence. But where are we going to get the value of full sequence? Right there. So full sequence will come from the sequence dimension of the key. So it will be k dot shape 2. Right. I should also store the k and v as a cache. So it will look like this. They are unused variable for now, but we will use them. Don't worry about it. We're not wasting anything. The same will go over here. Full sequence, full sequence. There is supposed to be no change. Mm, right. Full sequence. Full sequence. Now we have the same value of k and v as we were having earlier. So this step will remain same, and this step, if this step remains same, that is fine. Yeah, is casual, if causal. Okay, so the idea is for this KV cache attempt, we are going to have the value of t as 1, so we can actually make it false. We don't really need to worry about this part. The reason being, see, the mask is going to look like the triangle, but over here, there is only one new decoding token, so we don't really need this. So we can make it false, or a better version of this looks like make it true only if the value of t is greater than 0. Otherwise, everything is just like it should be like the way it was. So we are taking past k with an input, and we need to output a tuple of k cache comma v cache. We also need to change a signature. So this entire thing, I'm sorry, this entire thing is going to be a tuple. So it's tuple of torch.tensor and tuple of, I'm sorry, not this bracket torch.tensor comma torch.tensor. Maybe I should start coding in Z at this point. Not really liking it. But yeah, let's. This is not any better, but all right. Okay, so who is calling this function? Our llama block is calling this function, and hence it should also be taking past KVs as input. So we have sine, we have cos, we'll have past KVs as input, and this is going to be tuple of torch dot tensor comma torch dot tensor. I'm sorry, it is tensor, but tensor. And yeah, or it could be none, and by default it's supposed to be none. What it's going to output, it's going to output a tuple of, sorry, torch dot tensor comma torch dot tensor. This entire thing is going to be a tuple. So we just need to pass, like in this step of self attention, we just need to past kv, and over here we'll be expecting, okay, I don't think this is gonna work like this. So you'll have to say output of attention comma past kv or let's call it new kv as a self dot this thing, control X, control V, and we'll have attention out over here. Then we have the MLP, and then we have this. We'll return the new kv as the output. Now in the Llama model, we have the forward function once again. So yeah, things will change a bit over here. The reason is Llama model is a module list of Llama blocks. So for each of the Llama block, we'll have a KV pair. So here our past KV values will be a list of tuple of torch dot tensor comma torch dot tensor. And what is it going to output? It's gonna output the same thing. So I'll just copy this, control C, and I'll paste it here. And this entire thing is going to be a tuple. Okay, how did we do here? We have a none. So we'll just ensure this thing as well. We have none, and the default is none. So for each of the layer, we need to have this. So how the thing's going to look like here? Say we have like a new key value pair, which is a list because we need to return it. And instead of doing it like this, we'll enumerate over self dot layer, and we'll have a I as well. So now we need to directly go to these values. So we'll say, let's comment it. We'll say the past of this layer, though we shouldn't really care about past, but we care about it here. So the past KV values, let's take the ith index of it. And yeah, obviously the none check should be here, else it's going to be none. This is our layer pass. And we have this, we can pass it directly over here, past of this layer, and we'll get as output, we'll get like a new KV, and in the new key value pair, we can append our new KV. Cool. This is the logit. So I'll say logits are self.lm head, control V. We'll return the logits, and we'll also return the new KV. key values. Okay, since I said the value of t will be 1, so we need to change this index, otherwise the rotary embedding will assume the position is 0 at every point because it's from 0 to 1. So it will assume this. We need to have an idea about the length of the past. So past length will be, how can we get it? We can get it from the past key values. So this is a list. Let's take the first element. Let's go with key and let's get in the shape and the sequence length given by the second dimension, and the same check is not none, else none, nobody cares, right? Okay, it's an integer, so it should be 0. So yeah, if we have past length, we can say our past length to past length plus this thing. The value of t is 1, so yeah, who cares? So what effectively is happening is that sine and cos were pre-computed values here, right? In the rope, they were pre-computed indices. So we are just looking up these looking tables. So we need to tell what exact value we need to look up at, and we'll get the correct value. So yeah, it's done from this end as well. Now, who is calling this llama model is this generate function, right? Ideally, see, we have implemented llama from the scratch, and hence we had access to the forward function directly. We also have access to the forward function in GPT-2, but it's from Hugging Face and it internally handles the KV cache, so we don't really need to worry about it. And hence we'll be writing some if else over here. Now we're back here at the generate function. So let's see, right? Okay, one thing that I forgot to mention is that in after we have this concept of KV cache and things, so the zeroth step where the user prompt is being processed all at once, this thing is called prefill step. So I'll just mention it like this is actually prefill step, and from then on all the other steps are decoding step. Since all the tokens are getting processed at once, the per token processing speed in the prefill step is much higher than any like the consequent decoding step. The reason being all the tokens are getting processed at once, there is huge parallelism, of course, and assume that the same amount of time is being so not exactly same amount of time, but like the same amount of compute is being done or the time is being taken to process the rest of the tokens, and then it's outputting. And hence, generally the prefill step speed is higher than decoding step. Okay, so we have input IDs, we have encoded them. What do we need to do? We need to have like an output, like there is a potential that forward might return a KV cache or might not, depending on the type of model. So we'll just call it out. And if if the instance of out is a tuple, then possibly we can unpack it like this as past key values. Otherwise, that's the case of GPT. So the logits is just out, and the past key values over here will be none. So this is the case for GPT-2, and this is the case for Llama. Now in the same step, we need to keep track of everything that has been generated till now. And let's take this entire thing outside of for loop. So these all steps, they shall be out of our for loop and hence will look like this. And this step is now our prefill step. I forgot to mention it again. So this is like prefill step. We'll have logits, we have passed keys as none, and then in the for loop we'll get the next logit, of course, by the -1, and then the temperature scaling, and then the applying top p. I need to implement this, then softmax, then just sampling it, figuring out if end of token. We have generated now, right? We'll say generated dot append next token dot items. Okay, so we have list of everything that's generated, and like it has to happen something like this. If the past key value is not none, then our out will be model dot forward next token. We need to unsqueeze it along the batch dimension, and then we need to pass the past key values, and we are expecting logits and past key values from here, from the output. Yeah, it's done. This was the case for Llama, and the case for it will be very simple. Input IDs is just what was here, torch dot cat input IDs unsqueeze, same thing. Like this, we can uncomment it. We have input IDs. We can directly get the logits from here. Model dot forward. We have input IDs. That's what we are seeing. What do we say to the Lord of Death? Not today. Return tokenizer dot decode the same generated stuff. Comma skip. Oh my god, skip special tokens as true. These steps are not at all required. Can pass it. Let's just understand this thing once again. We have input IDs as token encoding. Input IDs as token encoding. Then we are doing a single pass over here. Then we are just figuring out. Then we go into the loop and we figure out the next logic. Next token, look at for end condition. Then we just append things. Then we have passed key values. Model forward was for a single element. Yeah, it is actually done if I'm not very wrong. I think I can start a terminal over here and I can try to look into this. Cool. So it works. That is what we were here for. So we just now need to go to our SSE generator over here. Okay, now we can actually yield each of the token at the same time. So what are we gonna do is we have inference queue, right? I'll exit this first. So this one is we have an inference queue. So assuming the queue is not full. So if the inference queue is full, We'll just yield data. We need to maintain the format. So error queue is not empty, rather full. Otherwise, we can get the async loop, uh, get a running loop. We'll have a future from loop dot create future. We'll have to put our request into the model. So we'll just call it request dot model dump, and then we'll pass it to the future once it's done, and our text will be await future. So we can directly yield the data and the done once it's done.